So we explained a very simple idea behind recursion, how recursion can work in place of iteration. Sometimes you should prefer one to the other, but you should know how to work with either scheme. And we're going to show both schemes now in computing n factorial. So n factorial is a mathematical quantity, how to build especially large numbers, and it's defined as 1 times 2 times 3 times 4, etc., up to n. As it then gets large, this gets extremely large. So for that reason, we're going to use the long int, because if we use a shorter int, we can't actually compute it for too long. Actually, long only allows it to work for up to 20. What happens past 20? You get what's called integer overflow. You get results that are incorrect because the number of bits available in a long on most machines is 8 bytes, 64 bits, and so for an integer type, it only able to represent factorial up to 20. So let's look first at something we should be comfortable in. We're going to do factorial iteratively, and we're going to accumulate the answer in the variable sitting there, long f equals 1. And then you're going to see in the iteration, it's your standard iteration. The beginning is at f of I equal 1. I goes up to and equal to n, auto increment I, and accumulate f by multiplying f by I. So you see, after you finish this iteration, you will have multiplied 1 times 2 times 3, etc. by n, the definition of factorial, and then you return f. That's the iteration. That should be straightforward. It should be no problem for you. Now, let's look at the iterative version. This is what's a bit novel. I'm calling it recursive factorial. Again, it's long. Int n doesn't need to be long because we can't, in fact, compute on very large numbers. And we check to see the base case. So here's our base case. N is equal to 1. What we know about when n is equal to 1, the definition of factorial is just 1. So we return 1. But if we don't have the base case, we can count backwards, and just as in our countdown program. Except here, we take recursive factorial of a smaller value times n. So this is the generalized case. This is generally what happens in the inductive case. N times the smaller value of factorial. You need to convince yourself that this gives exactly the same result. And that's what I've done here. In comparing both, I've just asked the user to say how many, and then I first do it iteratively, and then I second do it recursively, just to show that we're going to get the same result. So I've already compiled this. Let's run it. Why don't we do it for small number? So here's your iterative thing. Factorial of 1 is 1. Factorial of 2 is 2. 1 times 2 is 2. Factorial of 3 is 6. And again, you get the same results recursively. Let's do a slightly larger version. Let's do up to 10. And here the numbers start getting big. And you only see, because I didn't have enough screen width, this is the recursive version. You can see the final 10 is the same as this 10. And you can see how they go up. And you can see that since you multiply by 10, that's 10 times larger than that. Just like 3 to 4 is 4 times 6 is 24, 5 times 24 is 120, 6 and then 20 is 720, 7 times 720 is 5,040, etc. Okay, so that's a very standard example taken from mathematics. You get it straight out of a definition. If you saw a mathematical expression, you frequently see functions of this kind defined inductively or recursively. So there's a natural mapping. It lets you easily and algorithmically transcribe that idea into a recursive function. Okay, we want to examine yet another recursive function. And again, we're going to show how that recursive function can be written iteratively. And we're going to show in this particular example, which is the Fibonacci sequence, it's very famous, that sequence is defined as the nth element of the sequence is equal to the nth minus 1 element of the sequence plus the nth minus 2 element of the sequence, where the sequence initially starts with the 0th element being 0 and the first element being 1. So if you follow this formula, f of 2 would be 0 plus 1, namely 1, and f of 3 would be 1 plus 1, which would be 2, and f of 4 would be 1 plus 2, which would be 3, and so on. And what's interesting is, even though the numbers at the beginning look very small, the sequence grows exponentially. So here's a definition, doing it iteratively. I'm going to use longs because if I want, I can easily write something that exceeds a single precision integer. So I'll start off with f2 equals 0 and f1 equal 1. And here's where I add them together. f2 plus f1 becomes the new f2. And we retain the older value of the sequence in this step. And then after we make the summation, f1 becomes the f older value. And you can go to C and check that that will indeed compute this sequence. And we turn, for n, we have to compute it up until the nth element of the sequence. And then we return f2. So that's an iteration. But if you think about it, the sequence is more naturally defined with a recursion. And here's the recursion. If n is less than or equal to 1, then return n. That means if n is 1, then f of 1, the Fibonacci sequence at 1 is 1. Or if it was 0, the Fibonacci sequence of 0 is 0. And for our purposes, the Fibonacci sequence is only defined on the non-negative integers. Else, return the recursive call of Fibonacci n minus 1 plus a recursive call of Fibonacci n minus 2. So that's where we have a recursion. And indeed, both recursions count down. So in each call to this recursive function, we get 2 calls, and so on. So notice, if you have to go very deep in computing Fibonacci of n, you're going to get something like to the nth calls of this sequence in order to do the number of summations that you'll need when you get to a large value of Fibonacci using the recursive formula. And here I'm just going to ask you to print a table. I'm going to print a table with ordinary Fibonacci and recursive Fibonacci. Okay. Oop. I'm going to exit that routine, and now I'm going to execute it. I'm going to do a small value of n just to show us what it is. So, iterative Fibonacci, recursive Fibonacci. Answer 0, 0, 1, 1, 2, 1, 1. The third member of the sequence is 2. The fourth member, 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, and so on. And works very, very quickly. Let's do it again, though. Let's do it for up to 25. And we've zipped by on our screen a whole bunch of values, and then we can see that 15 is 610 plus 987, so we get 1597. Indeed, both the iterative and recursive give us the same answers as expected. But now let's look at a much larger number. Let's look at 45. Now look what happens. We've hit 40. The screen is slowing down. I'm working on a fairly modern Macintosh. All the answers are jibing. You can add the respective previous two to get this, but whoop, okay. It wasn't large enough. I'm going to do it once again because it started to slow down, but what if I do 50? Now you see at 43, all of a sudden the screen is frozen. We saw that it did 44, and that took a significant number of seconds. And now look at 45, it's still crunching. Crunch, crunch, crunch. Oh, finished. But you can see a noticeable lengthening of time. Now, I'm not going to let this run any further. I just want you to think about that. I'm going to abort this. So what is going on is on the recursive side, and if I had separated, and you can do this yourself at home, you could separate writing it iteratively from writing it recursively, and you could see you would readily get 45, 46, 50 until you got a number too big for the accuracy of a long integer, but it would run very quickly because it's a simple iteration and it's just a linear time set of additions in that sequence. On the other hand, calling it recursively means that we're going to ultimately end up with a bunch of ones being added, maybe a bunch of zeros, and those, for example, here we're going to have something like 4 million. So this is 4 million. So this is over 1 billion. And when you have over 1 billion function calls, you have a whole bunch of operations going on the stack and on calling a function, which is one of the more complex functions at the machine level that can actually take some few, maybe tenths of a millisecond, but still some significant time in relation to the simple calculation you're doing. So that's the pitfall. If you use recursion, it could lead to a significant slow up, even though on the surface it gives you a more logical, easier to understand program for recursive functions such as Fibonacci. Okay, the next major topic, and this is one that fascinates a lot of people, is to write programs that are recursive. So we'll look at a very elementary program that does it this way. And then later, in some further segments, we will very much make use of the technique and show you actual code and why you want to write code frequently, recursively. So the big thing about computation, what we know is, well, it's really useful, and it's really useful when you do lots of things over and over again. Big things. And that's why iteration is so powerful. And that's why we've paid a lot of attention to statements like the for statement and the while statement. They're very useful. And they're going to be even more useful when we come to our next big topic, which is going to be using them in relation to arrays and very large amounts of data. Okay, so we've seen how to do things repeatedly with iteration. I'm going to show you a simple example of doing that, and then I'm going to show you how the exact same thing can be done recursively. First off, in the iteration, we're going to write this little NASA program, little Cape Kennedy thing, where we have a countdown. We're going to decide that we need a countdown from whatever, some integer, for example, it could be 10. And here's how we might do it iteratively. So we might say while n greater than 0, printf time is, we'd print, for example, if it starts at 10 as 10, then we'd auto decrement, and then we'd keep printing that, so we do 10, 9, 8, 7, 6. The last value we print is 1, because after 1 it goes to 0. And then before we exit the routine, we print blast off. That's our iteration. We should be comfortable with doing that. We've already done a number of iterations. Now let's do this recursively, about the simplest recursion I can think of. We're going to call this routine void recursive countdown. Again, it's going to have this integer n, and may again start at 10. In the recursive case, we have a test to see if we're what we're going to call the base case. So if we're at the base case, n equals 0, and we're going to print blast off. If we're not at the base case, then we have to do the recursion. We do an else, printf time is whatever n was, for example, starting at 10, and then we call the function again, the same name function, but now we call it at 1 less. And we're going to keep on doing that. The recursion is going to keep printing this. It's going to do the else part until it reaches a value of 0, called with a value of 0. So it happens repeatedly. You have, as a key idea, a base case, in this case blast off at n equals 0, and then you have a general case, or the recursive case. And in the recursive case, you're doing a print of the time, you're counting 1 less, that's ensuring that it'll terminate, and you're done with understanding the most elementary of recursions. And if you've had some mathematics, if you're on the mathematical side of things, you'll recognize that recursion is very similar to mathematical induction. And one of the nice things about doing things recursively is they may be easier to debug or, in effect, prove correct. They may be more obviously correct. And as I say in the next video, we're going to show some interesting, again, simple but recursive programs. Okay, this is going to be the last major topic of C for Everyone Part A. And it's going to be the topic of how to deal with aggregate data. And after we're done with this topic, you can consider yourself a serious programmer. In some sense, the major programming languages of the first 2 decades of the real use of computers, namely the late 40s through the early 60s, had languages like Fortran and Algol, and these languages basically had, for aggregate data, the array type. So we are going to show how to deal with the simple one-dimensional array type in the C language. Now, so far we had multiple amounts of data. We would have to write out individual declarations. So we'd say something like int a, b, c, and so on for as many variables as we need. Or we could say, if they were somehow related, int a1, a2, a3, etc. But this is too limiting. First off, if we really need to do things for very large data sets, like we have to examine a colony of several thousand elephant seals, as one of our homeworks suggests, to find out their average weight, we don't want to have to write out thousands of individually named variables. They're going to be too hard to process, too limiting. Our way around this is to have the following kind of declaration. Int data, square bracket, 100, square bracket, semicolon. So as with a normal declaration, there's a type. This could be any of the standard types, like double, long, char. An identifier that should indicate what we're processing. I'm going to use the generic term in a lot of my examples, data. And then a size, which is an integer constant. It's got to be known at this point, partly because the allocation at this point would frequently be off the stack. When we perform that declaration, this is what the compiler produces for us. We get a one-dimensional array structure whose elements are data of 0, data of 1, data of 2, data of 99. Arrays in C start at 0. Some programming languages started arrays at 1, but 0 is the base address of this array. In some sense, data itself is an address in memory. 0 means the 0th element. So it's the index really at the, quote, first element that you're going to use in processing, whereas the last element is going to be whatever that size was. In this case, it had been 100 minus 1. So, in effect, these brackets with an index perform an address computation that starts at wherever in memory we have data. A normal cell, like int a, it might be stuck in memory cell 2004, and that's what it refers to. But here we have two parts in the memory calculation, and it's important to understand that this is a way to get what we call an address, because later we're going to talk about the relationship between array and pointer. And for more sophisticated work in the C programming language, you're going to have to understand addressing and pointer. But for very simple things, indexes and arrays are straightforward abstraction. So each of these items can store an int, and most machines that will be 4 bytes. Why is this so useful? Well, most processing is not about processing a few things. It's mostly about storing, retrieving, and processing very large data sets. Data sets that are frequently in the millions. Well, look at this little for statement. For I initialized to 0 or assigned 0, it's not initialized, assigned 0, I less than some size, auto increment I. Turns out we're doing a calculation here. We're summing. We're going to take the sum, it's the old sum plus whatever is in data. So by the time we get through that, we have added up all the data in that collection. Maybe we want to use it for an average, maybe we have other reasons to want to use it. But this doesn't matter. This one statement handles as much data as we have available to us. That's what's so powerful. And consider it as the canonical idiom for treating data when stored in arrays. And as long as you understand this and can make use of this, you're basically going to be a serious programmer. Now we're going to focus on the topic of arrays and how to initialize them, and especially how to deal with the concept of string. String is not a data type in the C language. It's really a series of characters. So a string is really an array of char, and we want to see how to initialize it. Of course, a lot of our interesting examples, including some in the homework, is to make use of working with strings. First, let's deal with the whole concept of array initialization. So we know that when we declare a simple variable, like here int SSN, we can, after the equal sign, which in this case is initialization, give it some appropriate constant value. But what happens when we declare an array? When we declare an array, we're actually declaring a bunch of variables which are indexed. And if we don't have an initializer, again, it becomes uninitialized. In some cases, the system will decide to automatically give you a 0, but you can't necessarily rely on that. But now, if you want to give your array specific values, and here you'd have an int array which has 5 elements. Don't forget, this means data of 0, data of 1, data of 2, data of 3, and data of 4. Then we can give an appropriate number of comma-separated values in this kind of list, the curly brackets. So in this case, data of 0 would be 1, data of 1 would be 2, data of 4 would be 5. But also, we can abbreviate the list. If we wanted all the elements to be 0, we could just list a single 0. We wouldn't have to list comma-separated list of 0. It turns out that all of the elements will be initialized to this value. And also, we can have an array where we don't specify the size of the array. So we just say int data, unspecified size, initialized by 1, 2, 3. And now the compiler says, there are 3 values. So that means they want a data, and this would have been equivalent to int data 2. And now data of 0 is 1, data of 1 is 2, data of 2 is 3. Okay, so, and depending on type, we would have such lists. So in doubles, we would have doubles. Now, what about the concept of string? Very, very useful. So we've already had strings. We've used them in things like printf and scanf. But strings are really what you might call concatenated together, sequentially next to each other characters, chars. So this string, AB, denoted by the string constant with the double quotes, is really, in its internal representation, the character A, a char, typically placed in 1 byte, the character B, a char, again in 1 byte, and what we're going to call the sentinel character, we're going to indicate that it's a 0, and it can be also written as single quote, \0, single quote. And the reason for that is if we have single quote, 0, single quote, we would not have a true 0. We'd instead have the ASCII value of the character 0. And that isn't a 0. So in order to have a true 0, we have to escape the 0 with this escape character, and then we get a true 0. So anytime you see a series of characters and the last byte being 0, that is an internal representation of an array. Let's look at something. Remember, we can also have an array, str, not give it a length, equal, and we can do this quoted string, and this is equivalent to having a series of inside curly braces, a series of characters. But look, there's a space there, I've drawn it, and a space there. So really, this is a character string that has, this is its first element, the letter A, a space is its second element, the letter B, a space is its fourth element, the letter C, and then implicitly the sentinel character. So what's that going to mean? That's going to mean, as an internal representation, A space B space C 0, the sentinel character 0. So that's really a 6-element char array. That would really have been char str6. Keep in mind that the space, single quoted space, has in the ASCII table, if you look up the ASCII table value, it's 32. So that's what would actually be stored in here, a binary representation of 32. So str of 0 would have the A character, str of 4 would have the C character, and then the final element of the string array, str of 5, would have the sentinel character 0. I call it a sentinel because when we do a lot of string processing, we generally put in a loop and it searches for the end of string. So that's why we call it a sentinel or sometimes a guard. It's a way to find the end of a string. So this has 6 elements. Okay, now we're going to go on to understanding more sophisticated ways of indexing and looping over arrays. Okay, now we want to get into the weeds. This is a difficult to picture set of ideas. Exactly how is an array stored in memory? And what we have to understand is an array has a place where it's stored, and it starts at what's called its base address. And that's because we want a bunch of elements. So we have to have a place to start, and then it runs contiguously through as much memory as is needed. And that gets allocated automatically in this case by the compiler. So there's some things we don't know explicitly because the compiler is doing it for us. And the array has a very strong relationship with another data type called a pointer. So we're going to start to explore the connection between array, address, and pointer. Now, a simple data type like an integer, when we say integer a inside a block, it means create a variable in memory, and the memory needs to be as many bytes as to store appropriately the values that are allowed for an integer. So an integer on most computers now is stored in 4 bytes. 4 bytes are 32 bits. And if we say something like a is assigned 3, then what that means is in these 4 bytes we put an appropriate representation, binary 3, and it's going to be in some location in memory. And remember, nowadays computer memory involves gigabytes. That's billions of individually addressable cells. So each of the cells in your computer memory has a location, which is basically a number. So for just the sake of having some concrete thing to think about, let's say this is location 7006, and we stored 3 there in this 4-byte set of memory cells. So when we think of a variable, we think of its name. That's how we use it in the code, but we think it has a location in memory, and inside that location is some stored value interpreted as an integer. Way to think about this is think of these things as, imagine a whole bunch of billion, and big computers it could be hundreds of billions of mailboxes. And in the mailboxes there are specific kinds of values. Integers, long integers, doubles, chars. Okay, so that's what we're going to store. We have a mailbox, it has an address, that's a number, and then inside there's something which is represented as a binary set of digits and interpreted as a particular data type. Now when we go over to an array as opposed to a simple variable, so let's say we have the array data 4, it's integer again, and we're going to store, remember we just talked about how we can initialize it. So this represents, instead of a single variable, 4 integer variables. And they start, again, if we view the compiler as having assigned them to the mailbox 7006, well, 2 is put in the mailbox 7006. 4 bytes later, at 7010, we put in 4. In 4 bytes later in 7014, we put 6. 4 bytes later in 7018, we put in 8. So we think of this array as having 4 individual cells, mailboxes, appropriate to that integer data type, meaning we need 4 bytes. And we can think of this as data of 0, data of 1, data of 2. There specifically is data of 3. And if you want to know how that address calculation happened, the address is equal to the base address plus 2 times the length of the 4-byte integers. So if the base address was 7006 and we need to be over here, well, that's 2 times 4, which is 8, so it's going to be 2014. That's an address calculation. So an address calculation for an array in C, base address plus the offset, the index, times the size required, the size in bytes required to store that individual data type. And that's what we mean by address arithmetic. And as I say, if these are unfamiliar notions, they do take getting used to. So it's something that don't worry about if you didn't get it. And some of you may not even need it. You'll certainly need it if you want to go on and do more computer science-y work. But if you just want to be a simple programmer, it may be enough to just understand that indexing works for you. But really, to get to the next level, you want to really understand the notion of address. Now, there are special variables called pointer variables. They're a derived type, and the type is expressed and follows. You say what the basic type is, in this case it was an integer. Then you use the special star character, the asterisk, and then the variable name. So frequently we'll use P for pointer or PTR. And here we're declaring a variable that can point at something that can store integers, but is in fact an address. So let's say A was an integer variable, a pure integer variable. This is initialization, and we're saying here, initialize this pointer to where A is stored, the address in memory where A is stored. Again, if you think back to my previous example, that would end up being 7006. It's something we don't have to know. The compiler is going to decide on it. The compiler could decide differently at different times in the compilation. So it's not something we worry about. But we have to understand that this is getting the address of this variable. And that address is being stored in P. So we can now think of P, it's this value 7006. What's stored in that area of memory is an integer variable whose value is 3, namely that was what we were thinking of as A. And now we can have as an expression P or star P, and those are two different variables. If we tried to print the value of P, we would get some address. If we were to dereference it, star is a dereferencing. If we were to dereference P, the value there would be the integer value 3. All right, all of that is fairly theoretical, a little hard to get your handle on if you haven't seen these ideas before, because you're really thinking at a machine level. You're thinking what the compiler does for you. But we're going to go ahead, and in the next segment we're going to write some code that will actually show what these values are. We're going to try to understand it by testing our concept, by actually writing code that prints an address, that prints what's stored at the address, and show that distinction in actual C code. So we're continuing with our understanding of pointers, arrays, and addresses. And what we're trying to show here is that while this topic is truly wonkish, in other words, it gets really into the weeds, very detailed in understanding how code functions at the machine level. Namely, you have to have a really good appreciation of memory as a resource and how it's allocated and how it's addressed. And one way to at least get some exposure to it is play around with code. So I just urge you to write your own variations of what I'm doing, just to make sure you get a real sense of what's going on. And here's a piece of code, and it's largely to understand some of the elements of how an array is laid out and how the machine accesses a memory cell and uses a memory cell in place of a name, and also the contents of the memory cell is yet something else. So in this program, it's a modification of one we earlier used, which was to allocate some grades into an array, and then we're going to sum up and average the grades. The sum variable is going to be a double, and here's where we get into this whole notion of pointer. So here is the pointer declaration. Double asterisk, so that's essentially saying double pointer to sum, and that's initialized to ampersand, which is address of sum. So sum has 0 stored at it. This is some address that at the moment we don't know, but whatever the address is in memory, and I'm going to print that out for you, so you're going to get a sense of this magic number, because it's the compiler that gets to decide where to put things, and that's going to be different from compiler to compiler, machine to machine, and conceivably even from run to run. Because on a big machine, many programs may be running, and there may be different parts of memory that get allocated to a particular program. So again, get used to, again, contextually, star here is not times. It's part of the declaration logic. It means pointer to double. Double star is pointer to double. Int star is pointer to int. Char star is pointer to character, which frequently gives rise to the notion of a string. Here's an ordinary variable, int I, and then we do the same thing we did before, which is calculate the grades, printing them out first, and then summing them, and then printing the average. And after that, we're going to look at where all of these variables are located. So I'm going to print out sum is at %p is the format for a pointer address. And a pointer address on a modern machine is displayed in hexadecimal. So that's not something you're used to. Hexadecimal is a base like base 10, except its base is 16, And because we run out of digits, we only have the normal 10 digits, we use the letters A, B, C, D, E, and F. F, in effect, is 15. But we're also going to print it as a long unsigned. So you'll see it more as an ordinary decimal number. And then we're going to print out the value that's found there. So look at what we're printing. Pointer to sum. So that's the value of pointer to sum is the address where sum itself is placed in memory. And this is the two versions of it. We get both the hexadecimal and the long unsigned. And then we do a dereferencing. Star in this case means dereference this pointer to double, which means look inside it and return a double. So ampersand as an operator back up here means address. Star down here means dereference. And you dereference a pointer variable and then you get effectively its contents. And what that is going to be is whatever the sum of the grades are. And then we're going to print that stuff out. And then we're going to further print where that array starts. So it says grades are at, and now we're going to also use, instead of hexadecimal, because maybe you're not used to it yet, we're going to use long unsigned, and it says grades go from long unsigned to this long unsigned. And this is the base address of grades where it was stored, and this is the address of the fifth element. And we'll find that it's offset by 20 because each element in grades is an integer which is stored in 4 contiguous bytes. Okay, so let's run that program and see that this all works. And again, I just want you to do your own experimentation. Here were my grades. Here was what the program ordinarily was going to do. This is the average. Sum is at. This 0x is the format for a hexadecimal number. And then we see a 7, an F, which remember is the digit 15, F, 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 5, C, which is the digit, I believe, 12. Or maybe is it C, D, E? Yeah, I think it's 12. And then B is 11, 12, 10. D is 13, 0. And this translates into a long unsigned as this very big number. So that's like the mailbox, that's the address. And stored there is the value 408. Notice 408 is the sum of 78, 67, 92, 83, 88. So indeed, that dereferencing of that pointer actually got us the same thing we would print if we had just printed sum at that point. And now look at how grades are laid out. Notice, let's forget all this beginning stuff because that's too big a number. It's located between 1920 and 1940, where sum was at 1904, and there was a variable like I. So if you think about what was being laid out in memory, there were all these individual variables. One was the variable sum, another was the pointer to some variable, another was I, and those were all 4 bytes. And then you come on where the beginning of grades is. So it all makes sense if you think about where things are laid out in that program. And then it goes up to 1940 because each individual element is 4 bytes long. And there were 5 elements, so you're adding 20 and you get to the last element. Okay, hopefully that makes sense. If that's too wonkish for you, you can probably skip this idea and still manage most of the work in the class. But if you're going to try to go on and you're going to make a heavy use of C and then finally C++, then this is a subject you want to try to master, and a way to master it is to do your own experiments. Okay, now we come to one of our most important topics, and this starts getting you way more sophisticated in your use of the programming language C. And what we're going to show is a sorting algorithm, a very simple sorting algorithm. It's called bubble sort. And while it's perfectly fine for small arrays, it's considered quite inefficient if you're going to use it on very large arrays. Now, sorting is one of the most important functions one does on a computer. Why? Computers are used for a lot of data. So let's take data in a phone book for a big city like New York or London or Moscow, where there might be many million of people. If those phone numbers and the people were unsorted, then it would be excessively difficult to go through and try and find somebody's phone number. Think about it. If you had several million phone numbers unordered, it would take you something like several million looks at that pile of information to come up with the right phone number. Or heaven forbid, if the person wasn't in that city, you would be hopelessly searching through every piece of information only to find that the person wasn't there. On the other hand, if you have the information sorted, then you can find that information in what we call log n time. Namely, if there's several million, then it might take you only 10 or 15 looks in that big phone book, in that big thick phone book, to actually look somebody up, because you're going to look towards the middle of the phone book and see whether you're past where the person's name might be, or you haven't come on it yet, and then you'd look in the next quarter of the phone book, and then you would get down to the right page, and on the right page you'd be able to also do an efficient search of finding that phone number. So by having information sorted, you have it also readily available for searching and looking up. And sorting and searching are so important that most important computer scientists of our era wrote a book, Don Knuth, and this book is called Sorting and Searching. So it's a volume just devoted to these techniques with very detailed analysis of them. And indeed, he even talks a fair amount about the bubble sort. Let me just read you. He says, perhaps the most obvious way to sort by exchanges is to compare two keys interchanging R1 and R2 if the keys are out of order, and then keep doing this, repeating it until, in effect, you have the information sorted. So these methods have been exhaustively analyzed because they're so important. And let's see how to do that now that we know how to have parameters passed. So a critical thing we're going to look at is swap, where the swap occurs between, in effect, what will be two out-of-order keys, A and B. And notice again that we're using our pointer parameters to simulate call by reference so that the two actual values can be interchanged. And we're going to, in this program, have reason to print out the array because we want to see that it's been properly sorted. And we see how we have a parameter for how many elements, the data that we're sorting, and then in this case, when we're printing the array, we're going to print it with a title, namely that character, the pointer to character, which we're going to call str for string. Looking at the routine, we first print using a format %s for string, the title, and then we go in, again, idiomatically. That's what you got to learn, these idioms. Once you master them, you can do most of your coding. You can do it very, very correctly and quickly. So for I, for I assigned to 0, I, if it's less than how many elements, auto increment I, and then print each element tab with a tab in between it. Now let's go to the actual bubble sort. We have the unsorted data at first, potentially unsorted data. By accident, it could be sorted. We want, again, to sort a certain number of elements. And we're going to need a double loop. So in the double loop, we're going to have two indexes, I and j. And I'm going to use a little trick because I want to show you how this works. So I'm going to use an integer, which is going to be a way to have the program stop at the critical point in the loop and only go on if we enter this particular integer. So look at this double loop. For the outer loop is for I equal how many, auto increment I. Then we're going to print how the array looks each time through. So for each I, we're going to print array, and notice our title. It's inside the bubble sort. And then I'm going to ask you to continue. After we've printed the array, in order to continue, you're going to have to enter something, a value for go on. You don't really care what that is. This is just a standard technique to halt the program. Now, you could halt the program other ways. Frequently, the system you have might have a very good debugger, and you can set breakpoints in which the debugger will automatically look at the program at particular times. But this gives us control, and we can see exactly what we need to see. We want to see for each step through the array, how does the sorting work? And then this is what's called the inner loop for j equals how many minus 1. We don't have to go the whole way. We advance j. We subtract j starts at 5. And then what this bubble sort is going to do is it's going to place the largest element in the array off to what might be called the extreme right. So each time through the outer loop, we get one more element properly sorted. And here's the sort. We see if two elements are out of order. If they are, we swap them. Okay, let's look at how main works. We're going to do it with a simple case. You can do it with something larger. One thing I'd recommend is take this, generate a bunch of data with a very large, for a very large array using random numbers to have appropriate data, and then see how this might work for a much larger data set. We're going to first print the array of grades. We've done that before. And then we're going to bubble it. And don't forget, internally to bubble, we've put that in effect debugging statement showing how the bubble sort works. And then when we're finally done, we're also going to print out the fully sorted list. Okay, so that's what we're doing. And let's see it work. Execute. So, just as in that program, the data started with it being out of order. 78 is too large. Excuse me, a message showed up that I'm not interested in. Whoop. Okay, so I've started the program. My grades are 78, 67, 92, 83, 88. Some of those are out of order. Then we've entered bubble sort, and then inside bubble, don't forget that was printing a title. We're using print array in each case. And now we've stopped. And it's saying, okay, this is what we see before we do any swapping. And now I'm going to input an integer to continue. And then the first time through, the swapping has swapped 67 and 78. And then 83 and 92. We went backwards, excuse me. Let's start that over. So 88 got compared to 83, they got swapped. 88 got compared to 92, they got swapped. 83 got compared to 67, it wasn't swapped. 67 got compared to 78, and they were swapped. Let's do it again. 92 got compared to 88, they were swapped. 88 is compared to 83, no swapping. 83 is compared to 78, no swapping, etc. And one of the inefficiencies of bubble sort is that even though we're already in order, it doesn't know we're in order. It has to complete the n-1 inner loops to make sure that things were out of order, because if the smallest element, the 67, had been over there, it would have bubbled down to the first element. You would have seen it occur throughout. So one of its inefficiencies is, and you could try to improve on this by seeing if you could check whether it's already sorted. You could have a flag and it could test whether any swapping occurred, and if no swapping occurred during a particular routine, you could stop right after that. That would indicate that everything was in order. And then my sorted grades are indeed 67, 78, 83, 88, and 92. Okay, why don't you play around with that program, and we're going to also show you some more advanced sorting techniques that are efficient, A, because this is such an important topic that you really need to understand it, and B, if you want to go on in computer science, or even if you just want to be informed, there's lots of fancy things and fancy programming that you learn by doing these more efficient and more sophisticated sorting routines.